Okie dokie. Strangers in the night. Here we go. Are you ready to learn? Yeah. Learning is your business. Business is good. Okay, game day. 100 points extra credit for anybody who goes to girls' game.
Are you ready?
No.
Extra?
Okay.
Yeah, extra.
Anybody that, how about plays in the girls' game?
Woohoo!
Alright, still no.
Don't crash the court.
Okay, so the second derivative parametrically has got a little bit of counterintuitive to it. There's a common mistake people make, and it's totally understandable that they make it. But if you give me a chance, I'll prove to you that misconception is foolishness and that you should never make it. So it goes like this. In order to get to the second derivative parametrically, I have to review a little bit or refresh your memory on notation. When you take the derivative with respect to time, you communicate that by virtue of the denominator of the Leibniz notation, right? Okay. Thirds pi over q. So that when you say dv dt, yeah, okay, on one level, it's differential, small change in volume with respect to small change in time, but it also communicates you took the derivative of what? V, and this denominator really communicates something else with respect to. Okay? So many levels to this. I love it. Okay, so the bottom communicates it's what it's with respect to. That's what tells you, oh, I took the derivative with respect to time. When you do the other side, at this point you know doggone well that you must use the chain rule when you get to the r and you pick up a dr dt. Because you're differentiating with respect to time and not r, you pick that term up, right? All review, correct? Okay. Say I, in order to provide or prepare for today, let's say, not provide, prepare for today, let's talk second. If I took the derivative with respect to x of both sides of this twice, then I would take the derivative with respect to x once, and then if I didn't simplify, then I suppose the notation would look something like that. The derivative with respect to x, the derivative with respect to x of y, and this would be the derivative with respect to x of the derivative with respect to x of x to the fourth. Notation-wise, if I were to clean this up then, the top is the derivative of the derivative, or the derivative twice over of y. And both times it was with respect to x twice, which we could then say that way, right? The other side is obviously whatever, 12x cubed, or 12x squared, that's not important. This notation, when you first learn it, when you're first semester calculus student, and it's all your teacher can do to just get you a basic clue, not lose you completely, okay? So they don't go here and say, you know what, let me explain why this one, the 2's there, but that one, the 2's there. Nobody's going to follow you there, okay? It's only after a while where you start to say, oh yeah, I kind of see that. I hope you do anyway. It's the derivative twice over of y, and both times it's with respect to x. So they really are different notations because they really mean different things. With respect to x both times, the twice over, we took the derivative of the y, all right? Let's look then at parametric equations. Keep this in the back of your mind as we go. Here we go. So in parametric equations, we talked about finding the first derivative, I dy dt over dx dt. Now we know, well, we can verify that makes sense, because if you clean it up algebraically, the reciprocal would come up and the dt's drop out. And we have our dy dx. Okay. Although, again, it feels like dy dx, it's really usually in t terms, which, as you probably know by now, that's no big deal. The derivative of y with respect to t is 4t cubed over 2t. Cleaned up then, maybe 2t squared. That's review. Are you cool? Okay, let's talk second derivative. To get the second derivative of y with respect to x, what will I differentiate with respect to? To get from dy dx to the second derivative, I'll have to differentiate with respect to x. Okay? So I'm going to differentiate with respect to x. Actually, I should write, first of all, the second derivative will be the result of differentiating with respect to x the first derivative. Wait. Notation-wise, that makes sense. That makes that second derivative of y with respect to x both times. Well, what is yield dy dx from previous work? 2t squared for this case, right? Well then, we're going to take the derivative with respect to x of that. What is the derivative of with respect to x of that? 4t dt dx, all right? Via chain rule. Okay? Now then, that is lame. I don't like that, and I don't know dt dx, and I don't want to go up here and find dt dx. What do you know? Dx dt. So this is equivalent to divided by dx dt. And that's the weird part. You're actually going to end up taking a second derivative, but then dividing it by dx dt. And as we go through, it's going to start to make less and less sense. I know I divide by dx dt. Remember, it all comes back to the chain rule. It comes from the chain rule. You have to do that. Well, what is dt dx? 2t. And so your second derivative is 2. No, I'll explain why that makes a lot of sense for this problem in a second. But, so we used the chain rule, didn't like the derivative with that denominator, or with that dt dx, so I moved it to the denominator, and we get 2. All right, now, let's go through with why this makes sense on 2 levels. First, if we were to eliminate yield, actually, let's do notation first of all. Notation-wise, this makes sense. Nope. Not ready. Let's go with eliminating the parameter. I could solve for t and say square root of x, but then I'd add the plus or minus. All right, so I'm going to do this a little differently, okay? Y is t to the 4th. And I think you'll agree that's t squared squared. Yeah? What's t squared? X. Okay. Don't overthink it, Elizabeth.
It's okay.
So, y equals x squared. So eliminating the parameter, we get y equals x squared. So although that's fairly complicated, y equals x squared, it makes a y equals x squared path. If we wanted to really get into it, the t squared t to the 4th and maybe make it move a little faster, all right, along the path. But it'd still be the same path. What's the first derivative and the second derivative? So surely that verifies whether we eliminate the parameter or do it parametrically, we get the same second derivative either way. Cool? Okay. Well then, let's talk about what we did here, and I'll also go back to why notation also makes sense here. When we did this, we started by, to find the second derivative, we first found the first derivative. And that was dy dx, but again, in our minds, it was t times, right? Then what did we do? We took the derivative with respect to x of that, yeah? Are you with me? Okay. Now, when we took the derivative with respect to x, it was actually up here, when I took the derivative of 2t squared, the first thing I got was 4t. So isn't that really like the derivative of the derivative, but with respect to t? Okay, so it's really like dy dt something's funky here. That's so good. I took the derivative with respect to t of 2t squared, which was was dy dx, right? Okay, sorry. I took the derivative of dy dx with respect to t, and that's where 4t came from, right? But then by chain rule, I also got this dt dx, which we put in the denominator. That then is the big idea that you want to probably box, is the second derivative parametrically is you take the derivative with respect to t of the first derivative, but then divide by dx dt. If you were to also verify that makes sense, notation-wise, this would be the derivative of y, and therefore derivative twice over of y, over dt dx, right? All of that over dx dt. Are you with me? If I then took that denominator up, it'd be the second derivative twice over of y with respect to t with respect to x times dt over dx, and that then is second derivative of y each time with respect to x. Okay? Notation-wise, it all hangs together, which you may not think, who cares, but in math, it's a big deal. Yes?
But for these equations, couldn't we just eliminate the parameter and then take the derivative twice?
Okay, so it's, first of all, you're assuming that you always can eliminate the parameter, which you cannot always do. Second, sometimes eliminating the parameter gives you this y-x equation is a mess. Imagine all the parametric equations that we've done. I mean, we've done kind of these listed juice problems and all that stuff, and we could do spirals. I mean, we could do a million different, there's these kind of questions. These are pretty simple in parametric. X equals t plus sine t, and y equals t plus cosine t. But without the parameter, the y-x equation is unbelievably, they're just a mess. And so that's why you want to be able to do both. I agree. A question like this, you're right, it probably would have been easier. Okay? But I chose it to illustrate the point so you can check. Now then, the big misconception, and the one that'll come back and haunt us in a little bit once the newness is worn off and you start to go trying to just think your way through it, you don't remember, is this misconception. When we found dy dx, we said dy dx is just take the derivative of y and divide by the derivative of x. And that works. That's exactly how we do it. Unfortunately, people then say, well, if you want the second derivative, you just take this, you take the second derivative of y and the second derivative of x and divide those out. Boom. Makes sense, right? Unfortunately, it doesn't make sense if you check it. Look at this case up here. If x equals t squared and y equals t to the fourth, then what is dy dt? Actually, let's just go. Okay, what is the second derivative of y with respect to t? 12t squared. What's the second derivative of x with respect to t? 2. Okay, so then, using our theory, what would the derivative of x, of y with respect to x twice over be? 6t. Well, obviously we know, by eliminating the parameter, it's supposed to come out 2. Well, this is most definitely not 6t squared.
It's 12t squared over 2, 6t squared.
So you're saying 12t squared over 2 is 6t squared?
Yeah.
Okay. Okay. Just checking. Okay. I can make you even doubt that. All right. Are you with me?
Yeah.
Now, you can also see notation-wise that this is garbage. Some people say, I don't care about the notation. I understand. But this this, you can see really quickly cleaned up that oops, this just doesn't wash notation-wise. This is this.
D squared T.
What?
D squared T. Oh, wait, sorry.
Yeah, okay. Times dt squared over d squared x. What does that come out to be? The second derivative twice over of y divided by the second derivative twice over x. Not with respect to x twice. Second derivative of x twice. And that's not the same thing. That's not the second derivative twice over with respect to x both times. That's not the same thing. Okay? Now then, let's try one or two in practice. Okay, so say you have a fairly clean set of parametric equations and you wanted the second derivative. Let's go. I know that I will first need the first derivative. What is first derivative? The first derivative. 3 over e to the t, right? You want to leave that as 3 over e to the t or 3 to the negative 1 t? Which one do you prefer? Do you care? Okay, so do we all agree with the first derivative? Okay then. The second derivative. The more you write this, the more you remember. So I'm going to say, again, you first take the derivative and take the derivative with respect to t, but then divide by dx dt. So if I take the derivative with respect to t of 3e to the negative t, I'm going to do that, and then I'm going to divide by dx dt, which was e to the t. What is the derivative of 3e to the negative t with respect to t? Negative 3e to the negative t over e to the t. So maybe cleaned up. Negative 3 over e to the 2t. Okay, so would that curve be concave up or concave down? Concave down. All right. Try one then. Speaking of concavity, now that you know how to find the second derivative, you can find the concavity of a path. Find the concavity of that parametric path of over 3. How did this go? Sorry, let me catch up to you. So, 4 cosine t over negative 3 sin t, maybe negative 4/3 cotangent t for the first derivative? Okay, the second derivative then is the derivative with respect to t of negative 4/3 cotangent t over dx dt negative 3 sin 2. So that's negative 4/3 positive 4/3 cosecant squared t over negative 3 sine t. I guess you could say that's negative 4/9 sine cubed. Negative 4 over 9 sine pi over 3 is root 3 over 2 cubed. So 8. I'm thinking negative 32 over
Oh, your DX.
27 root 3.
Your DXDC is like wrong. No, not it's not. How did you get side?
Oh, I combined the cosecant and the sine.
Yeah, apparently I don't know, paper.
Oh, that's unfortunate. Did somebody confirm negative 32 over 27 root 3?
Yeah.
Okay, that is less than 0, obviously, so the curve is concave. Okay, do you get the idea of second derivative parametrically?
Yeah.
Okay, alrighty then. Shall we go to homework questions or go over the test a little bit? All right, the homework, by the way, I'm going to say it in case I forget, the homework is due no matter what. I told the other class we didn't really have time to go over many questions, or any questions really. I told them as long as they have, okay. As long as you're not skipping more than, if you maybe have one blank, maybe two, okay. But any more than that, I'll be counting off for, okay? We'll go over questions on Sunday. We are just going over it, but not doing corrections. I do need these back. It is a six.
Wait, what's the scale?
James, pen, and yours back. I am still figuring out the curve. The first page probably will be 24 and above is no, 23 and above is an A.
CBEX.
Hey. I kind of have in my mind, this is a really good, something you really did well, this is what it is, and I'd say that's the.
CVAS, that's the fraction I used to, like Kayla, O is aluminum, P is.
On the first.
Kayla, Caitlin, not Caitlin, Mary, and then.
Oh, CBEX. Did you
Man, oh, I.
What's RSA?
Freshman after school club, but with a K. Yeah, no, that's our schedule. You stay 30.
I'm getting on the free schedule.
Oh, no. Yeah, you weren't.
I know.
So that's why we're doing this. So that's why we got Michaela, Olivia, Caitlin, Chris, Mary, and then Elizabeth. How some to get Starbucks about my Elizabeth. It's not me. Well, I go to swimming. I don't know about you. I never go. I know, right? You're like late all the time. Well, my sister, she's a good sister. Yeah, I'm just waiting for my sister to get stuff, so I can't leave it. So I always get stuff, which is great. Or you're here pregnant. Or you're here pregnant. What am I doing for that?
Okay.
I wait for my sister to be here so I can hang out and drink my water.
So the first page, I should probably pause this.